let's look at mole relationships. Now, we're not talking about relationships between furry creatures. We're talking about moles in terms of chemical reactions and different relationships between the amount of moles of different reactants and different products. And we can use those to predict amounts of products or reactants in a chemical reaction. This is something called stoichiometry. So let's start with what we already know. We know in a reaction of, say, magnesium and oxygen to make magnesium oxide, you balance it out, you have 2 magnesiums to 1 oxygen, and you get 2 magnesium oxides out. We've talked about this previously in the context of this means we have 2 magnesium atoms, 1 oxygen compound, and we make 2 magnesium oxide compounds. Just looking at the atomic level. But this also means something else. Same reaction, but this can also mean that 2 moles of magnesium reacts with 1 mole of oxygen gas, and we get 2 moles of magnesium oxide. So we need to remember what a mole means. A mole, remember, is just 6.02 times 10 to the 23rd atoms of a particular material. So if we before looked at single atoms, 2 atoms to 1 atom to 2 compounds, we can scale that up. Essentially all we're doing is multiplying each by 6.02 times 10 to the 23rd. But that makes a really big number, so we're just going to do it in terms of moles. So we're going to look at the molar relationships between all of these different pieces of our reactions. In order to do this, we need a way to organize some of our material, or some of our information. We're going to use something called BCA tables. BCA simply stands for before, change, and after. So prior to the reaction happening, what changes happen during the reaction, and what you get after the reaction has happened. The key to this is that we need to remember that our products and reactants don't exist at the same time. Our products exist first, our atoms rearrange themselves during the reaction, and then you get our reactants exist first, atoms rearrange themselves, and then you get the products out at the end. So let's look at an example. We reacted previously iron and copper sulfate, and we saw that we got iron sulfate and copper out of it. Now, there are a couple different ways that you could figure out those products. You could have Googled it, or you could have recognized that this is probably a single replacement reaction. So the metal is going to displace the other metal, and you're going to end up with your products. We started with approximately 0.4 moles of copper sulfate. That's the blue stuff that we massed out and dissolved in water. And we had excess moles of iron. We did that on purpose. We wanted lots of iron left over. And we had no moles of our products. During our reaction, we lost copper sulfate. Well, we didn't lose it, but it no longer existed as copper sulfate. All those atoms rearranged each other. So our change is that we're going to lose so many moles of copper sulfate. Now, that's all well and good, but what happens to the other things? Well, if we look at this, this is already balanced, and we have a 1 in front of each of these. This means that we have a 1-to-1 mole relationship. So for every 1 mole of copper sulfate that we lose, or is used up, we use up 1 mole, or the exact same amount of iron. So we lose 0.04, or we use up 0.04 moles of iron. And then we gain, because we're making these guys, the same amount. It's all a 1-to-1 ratio. So we gain 0.04 moles of iron sulfate, and we create 0.04 moles of copper. So that's the change. That's what's going on during our reaction. We're using up our reactants and we're making products. So we still have excess moles left after the reaction has happened. We saw that we had nails left over in our beaker. We had no moles of copper sulfate left over because our solution was no longer blue. And we ended up with 0.04 moles of iron sulfate that was still in solution, but it's not colored. and we ended up with 0.04 moles of copper, and you calculated this because you were able to mass it and then convert that into a mole. We could have predicted this if we knew how much we started with. We could have predicted how much we would get at the end. We just hadn't learned that yet. Let's look at a non-one-to-one mole relationship. So we've also reacted zinc with hydrochloric acid, and we know that we get zinc chloride and hydrogen gas out on the other side as products. If you balance this, it's a 1, and then here's my 2, and then there's a 1 and a 1. So we no longer have a strict one-to-one relationship between all of our compounds. So we're going to say hypothetically that we have 4 moles of zinc to start with, and we can say that we have excess moles of hydrochloric acid. Typically you have excess of one of them, at least for these first ones that we're going to do. And we know that before the reaction we have no products. So we have 0 moles of either of those. During the reaction, if we have excess hydrochloric acid, we're going to use up all of our zinc, and it's going to be made into something else. Question is, how much hydrochloric are we going to use up? Well, we have 1 mole of zinc to every 2 moles of hydrochloric acid. That means we're going to use twice as much hydrochloric acid as we use up of zinc. So we use 8 moles of hydrochloric acid. Now these, if we're looking and figuring out what our products are going to be, these are a 1-to-1 ratio. We have 1 zinc to 1 zinc chloride, so we know that we're going to gain 4 moles. And we have 1 zinc to 1 hydrogen gas, so we're going to gain 4 moles of hydrogen gas. So in our after, we have 0. We still have excess. We used up 8 moles, but we still have excess because we had lots there. And we produced 4 moles of zinc chloride and 4 moles of hydrogen gas. So if your question were to say, if you have 4 moles of zinc and you react it with excess hydrochloric acid, how many moles of hydrogen gas would you produce? Your answer would be 4 moles. Let's look at one more kind of tricky example. So here would be what your question would look like. So that might be what you see in your homework or on a quiz or test. You burn 2.5 moles of C3H7OH, that's isopropyl alcohol, in air. How many moles of carbon dioxide do you produce? So you could write the reaction. We know that when it says in air, it burns in air, we're reacting it with oxygen gas, that's O2, and we produce carbon dioxide and water. And then if you go through and balance it, we have our 2 isopropyls to our 9 oxygen gases. We produce 6 moles of CO2 and 8 moles of hydrogen gas, or water. So let's just say, well, our problem tells us what we start with. We start with 2.5 moles of isopropyl alcohol. Now, do you think we have a specific amount of oxygen gas? If you're thinking no, it's burning in air, it has essentially an unlimited amount of oxygen. So we can say that this is in excess. And right now we have no moles of carbon dioxide and no moles of water. So our change, we know we're going to use up all of our isopropyl alcohol. We've done this reaction before. You know that it will burn until you run out of isopropyl alcohol. So we're going to use up all of the 2.5. We're going to ignore the oxygen for right now because we know that we're going to have oxygen left over in the air. What we want to worry about is the carbon dioxide. We need to look at the ratio between the isopropyl alcohol and the carbon dioxide. It's a 2 to 6 ratio. 2C3H7OH to our CO2, which is really a 1 to 3 ratio. To CO2. That means for every 1 mole of isopropyl alcohol we use up, we're going to produce 3 moles of carbon dioxide gas, so 3 times as much. So if we were to type into our calculator 2.5 times 3, we get 7.5. Now this is really what we're looking for, so we could skip the rest and just say we produce 7.5 moles of carbon dioxide, and that would be our answer. But just for the sake of practice, let's finish out our table. Let's figure out how much water we produce. If we look at the ratio between isopropyl and water, it's 2 C3H7OH to every 8 waters, which is really 1 to 4. So we know that if we use up 1 mole of this, we're going to produce 4 moles of water. So we're going to produce 4 times as much water as we use isopropyl alcohol. So if we multiply 4 by 2.5, we get 10. So we know that in addition to our 7.5 moles of carbon dioxide, we would produce 10 moles of water. We'd still have excess oxygen left over in the air, and we would use up all of our isopropyl alcohol.